Greetings, AP Chemistry students. Today we're going to learn about a part of chemical kinetics called the steady state approximation. And this is a little bit of a tricky concept in some ways because it involves chemical equilibrium, which is a topic that we will be learning about in Unit 7. But it's something that I think you can grasp and understand here. And if not, there's some AP Daily videos that you can also watch that will maybe help you out with this as well. But for the steady state approximation, some reaction mechanisms have a first step that involves what's called a fast equilibrium. In other words, it involves chemical equilibrium, but it happens very fast. It's not your slow or rate determining step. Now, the thing about chemical equilibrium is chemical equilibrium occurs in reversible reactions when the forward reaction and the reverse reaction are happening at the exact same rate. Because in a chemical reaction that's reversible, if you start with just your reactants, you start going from reactants to products. But the reverse reaction doesn't happen at all because you don't have any products. It can't reverse from the beginning. And so the forward reaction starts happening. You start using up your reactant, so it slows down. And the reverse reaction starts happening faster as you have more products until you reach a point where the forward and reverse reactions are equal. That's called equilibrium. But all you really need to know is that the rates are identical at equilibrium. So what you do is you write rate laws for the forward and the reverse reactions. You set the rates equal to each other. You then solve for the intermediate that is formed in that equilibrium step and substitute it in to the following step for your slow step, for example. And that way you can figure out what the overall rate law for your reaction is and not have intermediates in your rate law, because intermediates in the rate law are not allowed. So let's look at some examples. All right, so in these examples, what we have is a reaction up here, and we want to determine if these reaction mechanisms are consistent with the following rate law. Rate equals K times the concentration of A times the concentration of B. So let's see if these three reaction mechanisms are acceptable. So for this first one, our slow step is the rate determining step. So we get the rate law from the stoichiometry of the slow steps. That would say that rate equals K times the concentration of A times the concentration of B. That matches the overall rate law. Now let's also see, do the elementary steps add up to the overall expression? Well, A plus B makes C plus M, and then M plus A makes D. So M is an intermediate. So we have 2A's plus B makes C plus D. So mechanism 1 checks out. For mechanism 2, our slow step is the second step, and our rate law would say that rate equals K times the concentration of M times the concentration of A. So that doesn't look like it's going to work out for us. But M is an intermediate which comes from the first step, which is a fast equilibrium step. And since it's a fast equilibrium step, what we can say is that the rate of the forward reaction equals the K of the forward reaction times the concentration of B. And then we can say the rate of the reverse reaction equals the K of the reverse reaction times the concentration of M. And since it is equilibrium, the rate of the forward and the rate of the reverse reactions are equal to each other. That's the whole point of equilibrium. So what we can say now is that the K of the forward reaction times the concentration of B equals the K of the reverse reaction times the concentration of M. And if we want to get M by itself, we divide both sides by the K of the reverse reaction So we end up with the concentration of M equals a constant, which is Kf over Kr times the concentration of B. And we can plug this in for M. And the thing is, if you take a constant and you divide it by a constant, you get another constant that we will just call K prime. So if we plug that in, we have rate equals K times K prime times the concentration of B times the concentration of A. And if you have a constant multiplied by a constant, you get yet another constant. So our new rate law is just going to say that rate equals K times the concentration of B times the concentration of A, which checks out with the rate law up at the top. Also, we need to double check that when we add all these steps together, that we get the overall reaction. Well, M is an intermediate that cancels out. X is also an intermediate that cancels out. Our reaction is going to be 2A's plus B makes C plus D, which is the overall reaction. So this is a valid mechanism. Now let's try reaction 3 down here. So in reaction 3, our rate determining step is the second step. So our rate law would say that rate equals K times the concentration of M times the concentration of A. But M is an intermediate, which comes from this previous step, which is an equilibrium step, where the rate of the forward and reverse reactions are the same. We can't use this as our overall rate law because you can't have intermediates in the rate law. So the rate of the forward reaction equals the K of the forward reaction times the concentration of A times the concentration of B. And the rate of the reverse reaction equals Kr times the concentration of M. These two rates are equal to each other. I'm going to change color so you don't get lost with what I'm doing here. So if we set these equal to each other, we have that Kf times the concentration of A times the concentration of B equals Kr times the concentration of M. So we just divide both of these by Kr. And we can substitute all of this in for M. And so this would give us a rate law that says rate equals, well, a constant times a constant over a constant is going to give us a constant times the concentration of A times the concentration of B times the concentration of A. Or rate equals K times A squared times B. So according to this mechanism down here, it would be second order in A and first order in B, which is not consistent with the rate law. So this mechanism is no good.